In this depth study, I will be attempting to answer the following inquiry question. Does antimatter matter? My hypothesis is that yes, antimatter has at least one useful function. I will be analyzing the applications of antimatter and the potential origins of the universe. Studying the origins of the universe is vital in understanding antimatter as a whole and why there is so little of it. Additionally, I will be explaining what antimatter is and some related phenomena that will be useful in understanding the applications of antimatter. During the conclusion, I will be summarizing all of the important information and judging my hypothesis based on the information that I have gathered. I will then be making a solid judgment on the inquiry question, backed up with reasoning and logic. The study of the origins of the universe has captivated physicists for decades. The most famous of these theories is the Big Bang Theory, which states the universe started as one immeasurably hot and dense point. This point would very quickly start expanding outwards, cooling down, and eventually creating the universe that we know today. This theory has gained traction due to the existence of measurable cosmic background radiation, which is mostly irrelevant to this depth study, so I'll keep it brief. Essentially, the universe started cooling down enough for photons to interact with hydrogen atoms, scattering the photons slightly. This scattering can still be observed today, several billion years after occurring. Many scientists have likened the patterns caused by the cosmic background radiation to that of a marker on a stretched rubber surface. This is the primary justification for the ever-expanding universe and the initial Big Bang, as there would need to be a unstretched state, so to speak. Many other theories do exist, however, they have less supporting evidence when compared to the Big Bang theory, and as such are widely disregarded. One such theory is the steady-state model. Very similarly to the Big Bang, the steady-state model suggests that the universe started in one point, but continued to create matter as it expanded. The Big Bang theory, on the other hand, implies that all matter is finite, diluting the overall density of matter in the universe. There is some merit to this model. However, the discovery of cosmic background radiation essentially caused scientists to abandon this theory as a whole. Another theory is the Big Freeze, which is more of a continuation of the Big Bang. This theory states that eventually, once the universe has expanded enough, all of the heat and energy in the universe will be evenly distributed, meaning that nothing will ever move again, and the world will just remain very slightly above absolute zero, meaning everything will just be frozen. After being frozen for a period of time, it is believed that the universe may possibly shrink back down to its initial size and start the process all over again. As an alternative to this, the Big Crunch is a theory where the universe will eventually collapse in on itself, creating another Big Bang. Both of these theories attempt to answer the origin of the universe in a cyclical manner, which may or may not be the case. We do not have any reasonable way to prove this with our current understanding of physics. Now, why does any of this matter? Well, antimatter was first theorized by Paul Dirac in 1928, while he was attempting to combine quantum theory and special relativity. When making it his equation, as you can see on screen right now, Dirac realized that there were two possible solutions to his equations, similarly to the equation the square root of 4. Within the laws of classical physics, this didn't make sense. Electrons could only have one charge, but his equation said otherwise. This led to Dirac denying the existence of what we would come to know as antimatter for some time. However, he eventually came to accept antimatter as a concept. These days, there is undeniable proof from as early as 1932, within 4 years of Dirac's initial theory, where Carl Anderson discovered the first positron. But what is antimatter exactly? Antimatter is matter that isn't matter. More precisely, antimatter can be defined as matter composed of antiparticles. An antiparticle can be defined as a subatomic particle which has the same mass as a regular particle, but opposing electrical charge and magnetic moments. An easy way to think about particles and antiparticles is to imagine them as balloons. For the sake of the analogy, the particle balloon is filled with helium, whereas the antiparticle balloon is filled with lead. This means that if we drop both balloons from 20 meters in the air, the particle balloon will float upwards and the antiparticle balloon will plummet to the ground. The opposite magnetic moment can be easily explained as having the opposite reaction to a magnetic field. In simple terms, antimatter is matter that behaves oppositely to matter in terms of electric charge and magnetic field. Every particle has its own respective antiparticle. For instance, proton and antiproton, neutron and antineutron, electron and, you guessed it, positron, neutrino and antineutrino, and of course, the photon and the photon. Yes, a photon is its own antiparticle. Photons are electrically neutral, meaning that they have no charge whatsoever. This means that if, theoretically, you were to get two photons and force one to be positively charged and the other negatively charged, they could be considered each other's antiparticle and have the relevant reactions to that. While neutrons similarly have no electric charge, one of the quarks within the antineutron is oppositely charged, making it a conventional antiparticle. The most interesting interaction to take note of is the process known as annihilation. Alongside sounding really cool, annihilation is the process that occurs when a piece of matter and antimatter collide. The result is a large release of energy, as both particles are eradicated from existence. The specific amount of energy released is equal to E equals mc squared, the very same equation that Einstein famously came up with, linking his special relativity to quantum mechanics, as Dirac had hoped to achieve. This reaction can cause the reactants to transform into something different. For example, when electrons and positrons collide, they typically create a photon. Fortunately, our universe is not doomed to annihilate, as photons also have the ability to become matter and antimatter if a sufficient amount of energy is present within them. This strange process is called pair production and can only occur at a quantum level. It can be more precisely defined as the conversion of gamma radiation into matter. The specific minimum energy needed for gamma radiation to transform is roughly 1.022 mega electron volts, which is roughly equivalent to 1 million electron volts. Using the equation E equals hf, where E is equal to energy, h is Planck's constant, and f is equal to frequency, we can determine that the minimum frequency of a photon that reforms matter/antimatter is equal to 1.002 is equal to 6.626 times 10 to the negative 34 f. Therefore, 1.002 over 6.626 times 10 to the negative 34 is equal to f. Therefore, f is equal to 1.51 times 10 to the 33 hertz, rounded to 2 decimal places. Pair production is a very important process, as without it, annihilation could theoretically annihilate the entire universe given enough time, though that is exceptionally unlikely considering how unbalanced the matter-to-antimatter ratio is. Additionally, elements of quantum electrodynamics are only possible because of the annihilation and pair production processes. For example, in this simple Feynman diagram, annihilation occurs at roughly the middle point, creating a high-energy gamma ray in this case a photon, which then reforms the matter and antimatter that it created, in a way. Additionally, in relation to the origins of the universe, assuming that the Big Bang theory is correct, some physicists have predicted that while the universe was very young and dense, there was an almost equal amount of matter and antimatter. Due to annihilation, almost all of the matter and antimatter were destroyed, dispersing energy around the universe, possibly increasing the rate of expansion, creating what we know as the universe. And all of the antimatter is mostly gone. There are still trace amounts in our universe, but not too much. This theory predicts that all energy in the universe may be a result of this massive annihilation. Physicists are unsure as to why this imbalance occurred, and researchers at the CERN Institute are currently testing out theories in the Large Hadron Collider. As of 2023, they are still studying the differences between the behavior of matter and antimatter in order to better understand possible reasons why this may have occurred. Alternatively, some physicists have rejected the entire notion that there was a significant imbalance of matter and antimatter, and instead that there was simply just significantly or insignificantly more matter than antimatter for whatever reason. Ultimately, and realistically, we have no way of proving either theory with our current understanding of physics. Returning to the hypothesis of this study, does antimatter actually matter? Well, as humans, we can't actually see the effects of antimatter with our naked eye, so in the average person's day-to-day, there really isn't much use for antimatter. However, it should be noted that antimatter plays a vital role in quantum physics and quantum electrodynamics, allowing for many core interactions, such as the conversion of light into matter, and the basic principles behind electricity. On a more human level, antimatter can directly benefit us. For instance, positron emission tomography, aka PET, is a medical technique which uses positrons to create a scan of the body. A non-harmful amount of a radioactive substance is inserted into the bloodstream, which then emits positrons during beta decay. The positrons annihilate with the natural matter in the body, creating energy, which is then measured, creating a scan of the body. This technology is especially useful for detecting tumors and/or cancer, as well as heart disease. On a more theoretical side of the applications, physicists have predicted that it is possible to generate electricity through annihilation. In theory, this process would be very, very effective. However, there are a few large issues. Firstly, the actual destruction of matter could end up being a significant problem for humanity, assuming we don't find a method of forcing the creation of matter. Secondly, the process of creating antimatter is presently very costly and electrically inefficient. Physicists predict that the amount of energy created through annihilation is less than 1/10 billionth of the amount of energy used to create the antimatter in the first place. Additionally, the total amount of antimatter ever created would not even be enough to warm up a cup of tea. As such, while theoretically possible, energy generation through annihilation isn't very realistic as of now. Another theoretical application of antimatter is using it as fuel for spacecrafts. Once more, using annihilation, physicists theorize that with roughly 10 grams of antimatter, a spacecraft would be launched from Earth to Mars within 1 month. This incredible speed would be extremely costly. However, if antimatter creation technology significantly improves, we may be able to explore our solar system much quicker, although it would have to improve very, very significantly, as the most antimatter we've been able to create currently is only a few hundred atoms. Additionally, physicists predict that if we were to launch an antimatter-powered satellite towards Alpha Centauri, the closest star to our own, it could end up reaching up to 10% the speed of light, which would allow us to explore Alpha Centauri's system relatively quickly when compared to conventional space exploration technology. Based on this information that I have gathered, I believe that my initial hypothesis is correct. Antimatter has a few theoretical uses and quite a few fundamental importance to quantum mechanics. During the Big Bang, at the very start of time, antimatter and matter may have annihilated to create everything we know, giving everything we know energy. This is, however, theoretical, so it cannot be used as definitive evidence to prove my hypothesis correct. So, as a more concrete function of antimatter, we look to quantum physics, more specifically quantum electrodynamics. Antimatter creates the fundamental reason that electricity works as it works. Additionally, going into the future, we could theoretically harness some antimatter annihilation power for space travel, which would be by far the most efficient way for us to travel space with our current understanding of technology. In conclusion, antimatter does matter.